Well, hello. Made a little video here for you that is going to demonstrate how to translate vectors back and forth in between what we call component form. I'll also refer to it as unit vector form. And probably the more traditional way, the way that a lot of you will know, and that's what I call magnitude and direction form. So this is components, or also called unit vectors. And we're just going to translate, I'll show you both directions, into the other form, and I just know to call this magnitude and direction. So I'll go into this assuming that you know a little something about what a vector is. There's some measurements that we make in physics where you have to include a direction for it to be complete. For example, velocity. It's not sufficient to say I'm going 50 meters per second. You have to say I'm going 50 meters per second to the right or to the left or maybe north or east. So when you need that direction, that's a vector property. So what we're going to do here is let's just imagine we have a vector given in magnitude and direction form. So that might sound like, let's use a displacement vector, 15 meters at 205 degrees. Now when we give angles like this, big numbers up in the hundreds, what we're saying is how many degrees counterclockwise from 0, and 0 to physicists points rightward or eastward. So the first thing I do is I draw this on a little coordinate system just so I have a picture in my mind of what this looks like. So I'll draw a kind of a light little coordinate scheme here, and I'll call this my XY axis. And 205 degrees would typically be counterclockwise from the positive x-axis. So you have to know how to count here. 90 degrees gets me to the y-axis, another 90 degrees gets me over to the negative x, and I need 25 more. So you see that math that I did there. So I'm going to draw an arrow at about 25 degrees beyond the negative x-axis. Again, beyond means counterclockwise. I'm going to label that there, 25. I got that by doing 205 minus the 180, which is where the negative x-axis points. And this will represent, this arrow, my 15 meters. So this might be somebody that took a walk and they said, okay, where did you end up after walking? Well, I ended up 15 meters at 205 degrees from where I started. Well, what is that in unit vector or component form? Well, the components describe what if you were to walk only in the x direction and then in the y direction. Like on a typical big city street, you can't walk through a building. You walk east-west or north-south. So what I recommend is that you draw those components first. So you go back to where you were starting. This is at what we call the tail of your vector. And you draw how far you have to go in the x direction. And so what I'm doing is I'm drawing what becomes the leg of a right triangle. Now be careful how long you draw this. And I'm pointing it towards the negative x direction, or leftward in this case. And then I'll go back to the tail and I'm going to draw how far I go in the downward direction. And that helps to have these lines on the paper here. That right there is how far I've moved in the negative y direction. So these are my two components, and they're all tail to tail right now. Now when we teach this in an earlier class, a lot of times we want you to put them head to tail because we like for you to be able to see that right triangle. But of course we could just slide this over or slide this down and we have our right triangle. Now this is a point where we're to a little geometry, or maybe trigonometry if you want to call it that. We need to find out how long each of these lengths would be in a triangle. So because we're working in degrees, make sure your calculator is in degree mode to do this. And I'm going to kind of rush through the trig here because I'll assume you've had this math. The 25-degree angle is up here next to the x-axis. And so the negative x component is adjacent to it. The adjacent side of the triangle is found with the cosine function. So I'm going to write here that this length is 15 meters times the cosine of 25 degrees. And then the component over here, the downward component, we could imagine it over here as the short leg of this right triangle. It is opposite the 25-degree angle, and so we would take 15 meters times the sine of 25, because the sine function relates the hypotenuse with the side that's opposite the angle. Now there's different ways to set this up. Some people might say, well, I'd like to use the 65-degree angle that's down here with the y-axis, and you can do that. Some would say, I'd like to draw it as a triangle. You can do that too. Some would say, well, I'd like to find the first side of this and then do the Pythagorean theorem kind of in reverse to get the missing leg. You can do that as well. I like this way because there's a lot less rounding error involved in it if you just do it like that. So you would grab your calculator, make sure you're in degree mode, and then do this calculation. And I've done it before, and I come up with 13.6 meters for the long one and 6.3 meters for the short one. Always make sure that your drawing is fairly accurate and that your components look about the right length. So that's what the components would be. Now, in the first class, if you took my class last year or one of the classes here, this is as far as we go. But now we're going to learn to describe unit vector form. And it's just kind of a shorthand notation, because really what this is saying I walk 13.6 meters in the negative x direction and also 6.3 meters in the negative y direction. Well, that's kind of a mouthful. And so what we do is we summarize in the negative x direction as negative I hat. And I'll show you how we write that. And in the y direction, we call that the j hat direction. So here's how we would write another name for this vector. We would say 13, almost wrote the wrong number there, 13.6 meters, and I like to put that in parentheses, and it's in the negative x direction, so we put negative and then I hat. It's I with like a little hat on top. I always put the negative out in front. Don't put the negative in front of the I hat or in between. It's going to look like subtraction, and that's just awkward. And then this one is in the negative y direction, so it would be minus 6.3 meters. Again, I'll set that off in parentheses. And then I put j hat because j hat means in the y direction. And the negative here means negative y direction. So that is the same vector named in unit vector form that we named up here as 15 meters at 205 degrees. So that's how you translate back and forth that way. So we could certainly go in that direction. This is going from magnitude direction to the component form. Well, what if you had instead been given the component form and then you had to figure out the magnitude and the direction? Well, now that we've got the drawing, I think you can kind of figure out what you do. You would just draw this. It would be drawing the components first. So you'd say, all right, set up a little coordinate system so you can draw a negative x and a negative y. So we're talking about the third quadrant. So I usually draw the third quadrant kind of big. And then draw your components, and you say, all right, if it's negative 13.6 in the x direction, you're going to represent that as 13.6. Make it a little darker. And then you also have a component in the negative y direction that's about half that big. So draw it about like this. So here's your 13.6, and here's your 6.3. Now again, if we're putting these vectors back together, when we first teach this, we say make sure that they're head to tail. I'm just drawing these vectors tail to tail just because it gets a little less cluttered on the page. And then, grab a different color here, you would imagine having these head to tail, they would meet right about there. So I'm going to draw my actual vector in that direction. Okay, so this is equivalent to the sum of these two red vectors here. I probably ought to be careful and put units on here. So if you only knew the legs of a right triangle and you needed to figure out what the hypotenuse is, I hope you would recognize that that's the Pythagorean theorem. So this would be equal to 13.6 squared plus 6.3 squared, and then square rooted. And of course, we already know what we're going to get here because I'm just working the same problem in the reverse. That's going to give us, within the limits of rounding, 15. Now, you're going to see, let me get a little more space here. One of the struggles people have, not so much doing the magnitude part, but doing the direction part. So one of the things to see is that you've got to be able to figure out one of the angles that this vector makes with one of its components. So in this case here, I like to always get the angle kind of going counterclockwise from the nearest axis. So what would that be? Now again, we have to know our trig functions, because we have at this point the hypotenuse length is 15, and we would have the adjacent side. Then you would use the inverse cosine of the adjacent side 13.6 over the hypotenuse 15. And that indeed will get you right back to, again, we've already seen this number, 25 degrees. So I'm just showing that you can go backwards or forwards doing this conversion process back and forth. So that is enough to get you through a lot of them. Let me show you one last thing that you might need to see. And that is, what if you're given something in component form that has a k-hat? And that's because in this level of physics, we start dealing with 3 dimensions. So things can move not only in a plane, like across the ground, but they can also fly up or maybe fall down through a hole. So let me just set up a little different problem like that. What if you're given a vector? We usually name our vectors with capital letters. Maybe vector A is the name of our vector. Looks like that. What if it is described as 5 meters in the positive x direction, and then maybe 12 meters in the negative y direction? So we put negative 12 meters j hat, and also 9 meters up, or in the positive z hat, or positive z direction. So we would write plus 9 meters, I think I said 9, and then you would do k hat. I don't know who chose I, j, and k for these. I mean, they're just kind of a convention that we use. And students all the time want to call them x, y, and z, and of course they correspond to x, y, and z, but we just use these I, j, and k with a little hat on it. So this one we can do in magnitude direction form, but we can't describe the direction. There's no good simple way to describe a 3-dimensional direction, which is why actually we have these 3-dimensional vector forms in unit vectors. But we can get the magnitude, and I sometimes just call it a souped up version of the Pythagorean theorem. So it turns out the length of this vector, if we were to measure it, and when we do a length, we draw the vector symbol and then we put a little bar around it. That just means the magnitude of it or the length of it. Here's what this looks like. It's the square root of, I'll leave the units out, 5 squared plus 12 squared plus 9 squared. So you picture drawing a triangle with kind of a third side, and so you get this 3-dimensional shape. And then let your calculator do the rest of that. This comes out to be 21.2. Put my units back on. That would be in meters. So magnitude of a 3-dimensional vector, piece of cake. You do it just like the Pythagorean theorem. So wow, this has gone 13 and some minutes. I want to stop here. This is far longer than I usually like to go, but hopefully this is enough to get you converting back and forth between component form and magnitude direction form, and you do just about anything you can see in an AP Physics class. All right, good luck with the rest.